Okay, we're on to part 2 of lesson 4D. Here's the homework from last night. If you want to stop that, see the different answers. Okay, so we talked about simulation yesterday. We at least introduced the idea again. Imitates a random, so it imitates, it kind of, simulates a random process that we get simulate outcomes that are consistent with real world outcomes. So they should be, similar. Describe how to set up and use a random process to perform one trial. Identify what you're going to record at the end of each trial. This is important to do. You perform many trials, of course, if you want to do a simulation, and then use the results to answer the question of interest. So in an attempt to increase sales, a breakfast cereal company decides to offer a promotion. Each box of cereal would contain a collectible comic book and feature a popular superhero, Flash, Batman, etc. By the way, we used to have cereals with prizes in there. This is very normal for it to happen. The company claims that 5 comic books are equally likely to appear in each box. That's their claim, but I don't know. A super fan decides to keep buying boxes into cereal until they have all 5 superhero comic books. The fan is surprised when it takes 23 boxes to get the full set. It's awful. Does this outcome provide convincing evidence against the company's claim that the 5 comic books are equally likely to appear? Maybe they just shortchanged one of them by accident or on purpose. I don't know. To help answer this question, we want to perform a simulation to estimate how common that is, right? Assuming the claim is true. So let's do that. So describe how to use a random number generator like randint or something to perform a trial. Describe how to set up and use a random process to record and then for one trial. And then again, identify what you're going to do. So we're going to number the outcomes here. You might get one of those comic books, 1 through 5. Generate a random integer from 1 to 5 that simulates buying the box of cereal and where they're equally likely. So you could just go random 1, 5. Keep generating integers from 1 to 5 until all 5 labels 1 to 5 appear. So you kind of just keep a tally, make sure you get all 5 comic books and stop when you get all 5. Record the number of boxes it takes. So make sure to write that last step. Record how many boxes it takes to get all 5. We carried out 100 trials and noted the results. The dot plot shows the number of cereal boxes it took to get all 5. So that'd be interesting. So, 5 times there, you only took 5 guesses. You literally got a different one each time. And then sometimes it took a little longer. You can see it skewed to the right there. Wow, it took one person 42 or 41 or 42. Wow, that's a lot of boxes to open. What does the dot at 18 represent? So sometimes I just ask you out one of those random dots, just make sure you know what it means. One trial where it took 18 boxes to get all 5 comic books. Of course, you're going to perform many trials, in that case 100 in the simulation. We want to perform a simulation to estimate the probability. We'll take 23 or more boxes. And we're going to use the simulation. So here's the simulation that was done for us here. So how many of those are 23 or greater? I don't see 23 on there, but I see 3 dots that are to the right of that, or more extreme than 23. So 3 out of 100, and I like the way they use the approximate symbol there because it's just nice. So 3 out of 100 is 3%. So be sure to use the simulation gives an estimate for the probability. So we're just kind of estimating the probability that it's not an exact probability. It's like the best guess we have, about a 3% chance of that happening. To help answer the question, we want to perform a simulation to estimate the probability. So based on the actual results of 23 boxes, is there convincing evidence that the 5 superhero comic books are not equally likely to appear in each box? So again, since 3 out of 100 were greater than that, that's less than 5%, that's 3%. Therefore, the probability that it would take 23 or more boxes to get it by when alone are, this provides, is low because that's less than 5%, so I like to think about that 5% as the mark of unusualness there. Like, what's unusual? Oh, we got something smaller than 5%. It's pretty unusual, right? So we do have convincing evidence that the superhero comic books are not equally likely to appear in each box, because 23 is just a very high number of boxes to have to open, according to our simulation. So local high school, 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery. Wow. 2 lucky winners are given reserve spots. I love that. Near the main entrance. The winning tickets are drawn by a student council member and a student council member from the AP Statistics class. When both tickets went to members of that same class, some people thought the lottery had been rigged because, AP Stats person could rig it. There are 28 students in the AP Stats class, all of whom are eligible to park on campus. Perform a simulation to estimate the probability that the fair lottery results in 2 winners from the same class. Describe how you use a table of random digits to carry out the simulation. So label the students in the class from 1 to 28 and the remaining students from 29 to 95. Numbers 96 to 99 will be skipped because we don't, and 00 because we don't have students that represent those numbers. Moving from left to right, taking 2 pairs at 2 digits at a time. Tell me come across 2 different labels from 1 to 95. The 2 students with labels will win the reserved parking spots. Record the winners, okay? Perform anything. So let's do this. So let's just kind of take it. So the first one there is 70 and then 84, right? So 70 and 84. That's trial 1. And then they went ahead and did 2 more trials because it said perform 3 trials. The first 2 numbers are 70 and 84. And then 10, 98 we're skipping, so 55. And then 18 and 19 for the last trial there. So what are we measuring here? So it looks like the first 2 trials resulted in not 2 people from the same class, but the last trial did get 2 people from the same class there. So 1 out of 3 is what happened there. In 9 of the 100 trials, both golden tickets were received by a member of the same AP Stats class. Does this give convincing evidence? So 9 out of 100, it's not that convincing. 9% chance, that's more than 5%. It's not that unusual, right? Because the probability is not small, it's greater than 5%, we don't have convincing evidence the lottery was unfair. Does this mean it was conducted fairly? Not necessarily, right? We just can't call it unfair. We don't have enough evidence to say that it's unfair right now, but we're not saying it's fair. It's different. When you are describing this in an A/B test, make sure to clear enough description so that the reader can get the same results from only your written kind of descriptions there. So you have to kind of, baby step it a little bit. Be sure to talk about, which numbers you're going to ignore, how many digits you're taking at a time, etc. Okay, so that's the lesson for today. Old Italian violins, especially those made by Antonio Stradivari, are supposed to have the best sound. Those violins are particularly prized, with some being sold for more than 15 million. Perhaps modern or new violins, maybe the new violins are just as good. Researchers designed a study in which 10 world-class violin soloists found to play 12 different violins. 6 of the violins were new and 6 were old, including a Strat. So the soloists were modified welder's goggles so they couldn't visually identify any violins as new or old. After playing these instruments in the practice room, 9 of the 10 violinists identified a new violin as the one they would choose as a replacement for their current instrument. Could the new violins really be preferred to old violins? We would like to perform a simulation to estimate the probability that 9 or more of the 10 soloists would choose a new violin. That's really interesting. So maybe new violins really are better, even though we have this, people are paying a lot of money for this really old violin. Describe how to use a random number generator to perform one trial of the simulation. So you could say, use rand int or something. 1 through 6 would be the new violin, 7 through 12 is the old violin. Kind of generate 10 numbers, record how many of each. How many are 1 through 6? Maybe you get something like this. So here's a simulated number. So, wow. So out of 100 simulated answers, so explain what dot at 9 represents. So that means that one person out of 100 had a result of 9 who chose the new violin, so 9 by chance. So there will be one trial. The dot at 9 represents one trial where 9 of the 10 soloists chose a new violin. So not 1 out of 100, but 9 out of 10 chose the new violin. Use the results of the simulation to estimate the probability that 9 or more. So that would be 1 out of 100, right? Or approximately 1 out of 100. Because only one dot is that or greater. D. Based on the results of the 9 choosing a new violin in your answer to part C, is there convincing evidence that new violins are more likely to be chosen? Because it's unlikely, less than 5% that 9 is only a 1% chance that 9 or more would choose a new violin. Does provide convincing evidence that new violins are more likely to be chosen. It makes me think new violins are better. That's the end of the lesson.